So, welcome. Today in this talk, we will be discussing the work of our recent paper. Specifically, we'll be discussing the machine learning methods that we used to search for parity violation and the generality of these methods and why we think that you should be using them too. And then we will also talk more specifically about our applications of these methods to the large-scale structure, specifically the BOSS dataset. So, some motivation for why we wanted to use this method. So, previous work looking at the large-scale structure used the 4-point correlation function analyses. We wanted to be able to look across larger scales to be able to consider points in localized regions of the space. And also the 4-point correlation functions are limited in the sense that the 4-point is currently the highest that can be evaluated. Higher point and end-point correlation functions quickly become intractable. So this method is also very scalable. With large amounts of upcoming data releases, this is really important, that the method can take in large amounts of data and still function in a reasonable timescale. In terms of previous applications of this method, so it was originally proposed for parity violation searches at the Large Hadron Collider using Atlas deposit data. It's then been demonstrated to work on images of snails because snails are a parity violating population because most of their shells spiral in a specific way. We here have now used it for the large scale structure, specifically the BOSS dataset. And in the future, hopefully there'll be many more applications of this and similar methods, because in theory, any dataset where you're searching for parity violation, these methods can be used. So in terms of considering the large scale structure, here we have a zoomed in region and we're treating the galaxies in the BOSS dataset as points from which we can then ask, are these points distributed in a parity violating way? So in this case, we have this localized region with some number of points, and when we are considering then parity violation, we are looking across this scale, this number of points. We also used some methods which were more geometric, still using the same machine learning process, and these are more directly comparable to 4-point correlation function analyses, where we can control the scale to look at points which are much further separated. So the method itself, how does it work? So actually, the method requires no machine learning to work. What we do is we construct a function f of this form, where x is the input data, and p is our parity operator, and g is some intermediary function. How this works is that G, the idea of this G is that this would encapsulate some concept of what it means to be parity violating in the system. When we then evaluate F on our testing data, it will return either positive or negative values, and these values directly correlate to the handedness that the system is associating to a given input. So, for example, positive may correlate with what it sees as left-handed, negative with right-handed, for example. So by then calculating the positive fraction of these outputs, we are gauging what fraction of the data the function f is assigning to be of a given handedness. So in this case, 50% would mean equal left and right handedness, and therefore no parity violation. For this to work, we need a good choice of G. If I choose an arbitrary G, I won't correctly encapsulate the parity violation of a system, and therefore I would just get a 50% output, which isn't very helpful. If I know my system, so for example over here we see parity violation in the sense that we have these local groups of 3, and there are more of this type in blue than the red type. So in this scenario, I could construct some function g, which could be consider local points beneath some scale and compute the mean and some ordering of internal angles, for example. And I know that for this setup, that would work. The blue points would return say positive values, and the red ones negative values. So I would get this ratio of 2 to 1, which would tell me that 2/3 of my data set is of a specific handedness. However, in general, we don't know our system. We are searching for parity violation. We have no concept of how it would exist in the data points. And so we need a way to find an appropriate G. And this is where the machine learning comes in. So how does the machine learning work? So what we do is we construct this loss function here. So we are basically optimizing f to be as far away from 0 as possible. This has the result that we are training the network to conceptualize what it would mean to be parity violating in this data set. So for the training data, it learns some concept of what it would be to be parity violating. We can then evaluate this on the test data set to see if this concept of parity violation is realized and if there is some difference between what it has learned to be the handednesses for this data set. So as I mentioned earlier, the first real application of this method was for Large Hadron Collider data. The idea being that in LHC deposit data, there could be traces of parity violation that we are not currently finding because we're not looking for them. So in this method, that is at Atlas, we have these projections of onto the cylinder, and from these we could form potential inputs for a convolutional neural network. The full idea and proposal of this is given in this paper here by Lester and Toombs, so I recommend taking a look at that paper also. So then we come to the snails, and this is a very interesting application. It really demonstrates the generality of this method. The concept here is that the majority of snails have a specific handedness in their shells. So images of snails are a parity violating data set. And so in this case, the network was trained on large numbers of images of snails. And then the network is learning something about what it means for an image of a snail to be parity violating. So understanding something about the geometry of the system. We can then evaluate this on the testing data, and it successfully detects parity violation. There has been some analysis in this, which you can find here, and it demonstrates that this network really is very general. Yes. So now we come to the large scale structure. So here we have some sample images, each coming from different data sets. And the idea here is, can you see parity violation better than the neural network? So if you want, you can pause the video and have a quick look, see if you can see any features that might lead to parity violations. Yeah. So looking at these, this first image actually comes from a data set of randomly generated images. So when we evaluate when we train our network on these images and evaluate them, we find no parity violation. So 50% means we have an equal number of what the network assigns to be left and right-handed objects. In this image here, you may be able to see that we have some more of these groups of 3, and the network detects as 100%, which essentially means that every image in this data set is given the left-handedness, which in this case is because every single image, every point in this data set was contributing to that parity violation, and so every image is of this type. Here we have random background field with MNIST image overlaid, and this also is parity violating because the MNIST dataset is parity violating. In this case, we detect at the 90% level. And this final image is maybe a bit harder to see, but if I change the colors, you can maybe see that we have this spiraling object hidden within the points. And in this case, with similar such images, we detect this 85%, which these numbers here are really representing what fraction of the data set the network is seeing as having the dominant handedness. So we also used color convolutional neural networks to encode 3-dimensional information, and we worked with 2D and 3D geometric methods, as well as a 3-dimensional vector-based method. So these methods all worked on the same fundamental principle, we're just changing the input types. But the full analyses using these methods can be found in the paper. So finally, results in the large-scale structure. So as I mentioned before, 50% output means that the network has determined that there are an equal number of what it sees as left and right-handed objects. In this case, we see that for every single method that we used, for all the variations, we get numbers which are undistinguishable from 50%. So we have no significant evidence of any parity violation in the large-scale structure, which is at odds with previous work, but we can find no evidence to support any claims of parity violation. So to summarize, we looked at this method that we used for machine learning to search for parity violation. We showed this method is very general and can be applied to any system where we're searching for parity violation. We discussed specifically our findings in the large-scale structure and how we were unable to detect any parity violation, despite extensively showing that the method has the ability to detect parity violation where it exists. For the full analyses, please go and check out our paper, either at this link or following any of the QR codes on any of the pages in the presentation. In terms of the future, They've got lots more data coming soon with DESI, Euclid, and Roman. So the upcoming data should be continued to be investigated using these similar methods. We also proposed that it would be useful to find some kind of 3D convolution as a general searcher of local patches of space as an extension beyond the color convolutional neural networks. And finally, it would be very useful to make direct comparisons between these methods and the 4-point correlation functions. So for example, testing the performance of the 4-point correlation functions on some of the test sets that we used to show that our method works, and to see if they both methods perform equally well at detecting different types of parity violation. So thank you for attending the talk. I encourage you to take a look at our paper in full. And yes, thank you very much.